Alrighty, folks. So moving now kind of into the second portion of Unit 2, we're going to start shifting into looking at radical and rational functions. Radicals will be today, well, in this lesson, and rationals will be in the next lesson, lesson 5. But finished up, well, I mean, they never really go away completely, but wrapped up our focused part where we were looking at polynomial functions. So here, as always, are kind of the big ideas, a little checklist to come back and check in with yourself. The important skills, the big ideas for the lesson. Have you got them, or do you need a little more practice, or maybe need to reach out to me and go over some stuff? All right, but let's jump right in. Starting off here with a radical function. What is it? And before we even talk about that, let's just remind ourselves of what we mean when we say a radical. So a radical expression, remember, that's just one where we're taking a root of something. So like a square root or a cube root or a fourth root, etc. For this portion of Math 30-1, and really for most of Math 30-1 where we're looking at this radical stuff, we're actually mostly, pretty much entirely, to be honest, going to focus on square roots. So remember, all a square root is doing, what a square root means, it takes a number or an expression and it says, what number could be multiplied by itself to give this as the result, right? So for example, the square root of 4 is 2, because we're saying what number, if we multiplied it by itself, would give us 4? Well, the answer is 2, right? 2 squared would give us 4. 2 times 2 would give us 4. So the square root of 4 is 2. 2 multiplied by itself is 4, right? 2 times 2, which is 2 squared, gives us 4. In other words, square roots are just the inverse operation of squaring. They're like unsquaring, right? 8 squared is 64. So the square root of 64 is 8. So we call that thing, the expression that's having its root taken, we call that the radicand. That's just a term that will come up often when we're dealing with radicals. So 4 is the radicand here. It's the thing we're taking the root of, right? If I had root x, then whatever x is, that's my radicand. So in Math 20-1, you would have studied radical expressions and radical equations. You would have dealt with both. So for example, right, an expression, remember, it's not equal to anything. It's just, well, it's an expression, right? This could take on many different values. It depends on what we make x, right? If I make x 1, then this is the square root of 75. If I make x 2, well, then it's the square root of 75 times 2 to the power of 5, which is 32. So it's some bigger number, right? But there's not like one correct value for this. It depends on what we put in for x. Same goes for this. This isn't equal to something. There's no correct x or correct y. We can put in whatever we want. Then we looked in Math 20 at radical equations and how to solve those. These really do have one correct value. Well, maybe not one always, but some correct value or values of x that could make this true, right? You can't just pick whatever number you want and this is going to come out to be true. There are certain values of x that solve the equation. It's saying the square root of 3 times some number plus 3 needs to be equal to 5. Not every value of x is going to make that true. Only a select few can make that equation true, right? Now, all we're going to do in Math 30-1, we're kind of going to extend this a bit further, and we're going to look at radical functions. I mean, you know what a function is. We've talked about them pretty much in every lesson since we started Math 30, and we will continue to do that for pretty much every lesson until the end of Math 30, okay? Like any other function, a radical function just involves an equation into which we can input x's and the equation will output y's, right? That's what a function does. You input values of a variable, it will compute the associated output, okay? Now that equation, all we're doing here for radical functions, you can probably guess, is just that the equation involves a square root operation. So that equation just also involves square root operations being performed on the x. So the simplest, most basic example of a radical function would just be y equals the square root of x, or f of x is the square root of x. But you can see this works like any other function. We're going to input x's. This function is going to take the square root of them, and the result is our output y, right? So here is the graph of y equals the square root of x. I mean, it checks out, right? If I input 0, the square root of 0 is 0. So when x is 0, y is 0 for this function. If I input 1, square root of 1 is 1. So when x is 1, y is 1. Here, when x is 4, I take the square root of x, so the square root of 4, my output is 2. So the point 4, 2 will be on the graph of y equals root x. Put in 9, square root of 9 is 3. So the point when x is 9, y will be 3. That point should be on our graph, right? X is 16, square root of 16 is 4. Take the square root of x, you get your y, right? Notice all of these, this is just the square root of 16. This is just the square root of 9. This is just the square root of 4. That's what our function does. It takes the square root of the input. This is a radical function. It's the most basic radical function we can come up with, right? It's just y equals the square root of x. Okay, now talking about radicals, we kind of can't talk about them too long without bringing up their restrictions. And you can even tell from the graph of y equals root x that we're looking at here, it looks like x cannot be any real number, right? It looks like x exists over here. Well, x is valid over here as an input, but it stops here, and therefore our y's also seem to kind of stop there. They don't go below 0. Let's remind ourselves of why that is for a radical function. Don't forget, a square root is a way of saying what number can be multiplied by itself to equal the radicand, right? Again, the square root of 4 is 2. Why? Because 2 times itself is 4. 2 times 2 is 4. 2 squared is 4, so the square root of 4 is 2. Okay, so when we're dealing with a square root, what we're really saying is what could I multiply by itself to give 4? That's going to be key for understanding where these restrictions come from. Because if you multiply a positive number by a positive number, maybe that positive number is itself, right? If you have a positive number, multiply it by itself, that's a positive times a positive. What happens if you do positive times positive? You get a positive answer, right? Positive times positive gives you a positive answer. All right, what if you do a negative number by a negative number, right? Maybe, negative 3 times, well, let's just do it by itself. Negative 3 times negative 3. You get positive 9, right? A negative times a negative is also a positive. So we've kind of tried both ways you could multiply a number by itself, right? If you multiply a positive number by itself, you're doing a positive times a positive. If you do a negative number by itself, you're doing a negative times a negative. And either way, for both of those possibilities, you end up with a positive answer. So if you multiply any number by itself, what will the result be? Positive. There's no way to take the square root of a negative number because nothing times itself could ever be negative. If it was negative, we square a negative number, we get a positive answer. If we square a positive number, we get a positive answer as well. So no number can be multiplied by itself to give a negative answer. So taking the square root of a negative number is impossible. It just doesn't make sense. Nothing times itself could ever be negative. Or we might say it's restricted because no number times itself equals something negative. Now, small caveat here, it's not part of the Math 30 curriculum. I should really be saying no real number times itself equals something negative, which for us essentially means no number that we will ever deal with in Math 30 can be something negative. But fun fact, there is something called an imaginary number. I know that sounds like a joke. It's not. It's actually a term that we use in mathematics. There are these things called imaginary numbers that can do this, where they allow us to take the square root of a negative. But that's for in your university math careers if you are headed that way. Okay. Anyway, so for this reason, right, because we can't take the square root of a negative, the domain of a radical function is always going to be limited to only include values of x for which the radicand is greater than or equal to 0, right? It can be 0. The square root of 0 is just 0. But the square root of a negative number is undefined. It has no meaningful definition, okay? So take a look here, right? We were doing y equals the square root of x. So what does that mean? If we're not allowed to take the square root of negatives, what is the domain? What x's are we allowed to put in? Well, we could see that our domain would just be all x's such that x is greater than or equal to 0, right? All x's such that x is greater than or equal to 0, and that will guarantee we're not taking the square root of a negative number because our domain is only x must be greater than or equal to 0. Well, look at the graph. Hey, that checks out. X starts at 0, right? Our valid inputs, the lowest one is 0, and then as long as we're above 0, we can always just take the square root of that number. It's when x is negative that the graph stops existing. We can't put negative x's into this function. So the function's graph stops there, right? It doesn't go below 0 on the x-axis. And that also explains why the range is y must be greater than or equal to 0, right? Because if the smallest x can be is 0, well, then we could do y is the square root of 0, which is 0. But how is y ever going to end up negative? Well, it's not, right? There's nothing that we could take, no positive number that we can take the square root of that ends up giving us a negative answer. So it kind of checks out. If the smallest x can be is 0, then yeah, the lowest y can go is 0 as well. It's not going to dip into the negatives here. As x gets larger, so will y, proportional to the square root of the x. But yeah, our domain will be all x's such that x is greater than or equal to 0. And as a result, our range is all y's such that y is greater than or equal to 0. Okay, let's try practicing this, seeing if we can figure out the domain of each of these radical functions. All right, so here we go. First one up. Hey, we just did this one, right? Why do we get restrictions when we have a radical? Because we can't take the square root of a negative. So looking at our radical here, what are we taking the square root of? We're just taking the square root of x. So our domain, we'll first figure out what what are we dealing with here? It's just that x needs to be greater than or equal to 0. We can't take the square root of a negative, so that's the set of valid x's that we can input into this function. So our domain would just be the set of all x's such that x is greater than or equal to 0, and x is an element of the real numbers. All right, now look at this one. Now a very common student mistake here, folks, is just to say, okay, there's an x in a square root, so x has to be positive, right? No, the square root, what we're taking the square root of, the radicand overall has to be greater than or equal to 0, right? It's not just that x has to be greater than or equal to 0. It's totally possible that x might be able to be negative, or maybe it needs to be greater than or equal to 3 or something. We need to choose our x's so that this overall radicand, this 2x minus 3, is greater than or equal to 0, because that's what we're taking the square root of. Not just x, we're taking the square root of 2x minus 3. So start there. We'll say that 2x minus 3, that's what we're taking the square root of, so that needs to be greater than or equal to 0. Add 3 to both sides, and we'll see that 2x needs to be greater than or equal to 3. Divide both sides by 2, and we'll see that x needs to be greater than or equal to 3 over 2, or 1.5 if you prefer, but I think a fraction is a perfectly good way to do it here. Okay, now notice, right, not greater than or equal to 0. It actually, if x was 1, you could see we'd have 2 times 1, so 2 minus 3, which would be negative 1, and we'd be taking the square root of negative 1, which wouldn't make any sense. So see what I mean, right? It's not just that if there's an x in there, x has to be greater than or equal to 0. Overall, the entire radicand needs to be greater than or equal to 0. So that makes our domain for this one the set of all x's such that x is greater than or equal to 3 over 2. X is an element of the real numbers. Of course, you could also do it in interval notation. So x could be anything from 3 over 2 all the way up to infinity. For that, I should clarify it's a domain. Okay, and there we go. All right, last one here. Again, we're taking the square root. Why does that give us restrictions on our domain? Well, because we can't take the square root of a negative. So what are we taking the square root of? 5 minus x, right? So 5 minus x needs to be greater than or equal to 0. In this case, I'll just add x to both sides. That seems like the easiest way to isolate and figure out what's true for x. So 5 must be greater than or equal to x. Another way of saying the same thing, just because we're used to putting our x's on the left, we could say x is less than or equal to 5, right? If 5 needs to be greater than or equal to x, then x needs to be less than or equal to 5. Okay, saying the same thing, just kind of two different ways. So our domain then would be the set of all x's such that x is less than or equal to 5. X is an element of the real numbers. Okay, now notice there, again, see what I mean? X actually could totally be negative here. Because if x is negative, that we're doing 5 minus a negative, that's not going to make our radicand negative, right? So don't fall into the trap of thinking, okay, if I see an x there, it's just got to be positive. No, overall, the radicand has to be positive. We have to work out what that means for x. But there we go, right? Domain for radical functions, to be honest, pretty much, I mean, 99% of the time, it's just going to come from the fact that the radicand can't be negative. So we figure out what x's would make it negative. Those are restricted x's. Rather, what we usually do is figure out how to guarantee that x is greater than or equal to 0, and that is our domain. Okay, let's move on to transforming these radical functions now that we've introduced ourselves to them. All right, so this is kind of a recurring theme in Math 30-1. We're going to find many functions along our way. We're going to learn new functions, see how they work, and then we're going to transform them. So honestly, folks, this is really nothing different than what we did in Unit 1. We're going to go a little bit deeper with it and think about what it means specifically for a radical function, but the core ideas here are the exact same. You're going to be kind of sick of this by the end because we're going to do this for pretty much every function we talk about. We're going to learn a function, think about what it's doing to our inputs, and then we are going to transform it. But every time we transform it, it's going to be the exact same set of skills we used in Unit 1. Okay, so everything you did in Unit 1 for transformation also applies to radical functions. In fact, there were examples in Unit 1, or examples from your practice questions and in the notes, where we were doing it to radical functions, and we never skipped a beat, right? We just did what we always did. So you've actually kind of done this already. We're just going to go a little bit deeper and think about, specifically the radical functions here, but it's the same stuff. Okay, so recall that we can represent transformations to a graph or to a function in the following ways. Okay, in function notation, we've got this y equals af of bx minus h plus k. Sometimes it's written with the k over here. They subtract k from both sides. Honestly, as my first step when they write it this way, I just add the k back over anyway. This just makes it a little more intuitive to me and easier to pick out, but just be aware sometimes they do write it this way. Okay, but again, right, looking here, reminder of all the stuff going on. It's just saying if you want to transform f of x in certain ways, you could take that equation f of x and change it in the ways described here. This is just general. This is saying to transform any function f of x. You could replace x with b times x minus h, then whatever that is, multiply it by a and add k to it, okay? Reminder that a causes a vertical stretch by a factor of absolute value a. Okay, so it vertically stretches it. All y values get multiplied by that a. And a vertical reflection across the x-axis if a is less than 0, if a is negative, right? If it'll flip it upside down across the x-axis, right? Again, it just takes all our y values and multiplies them by a. We see that in our mapping notation here. Mapping notation, remember, that's a little more specific to exact instructions on how to go from a certain point x, y on the original to an image point on the transformed graph or transformed function. Right? So you can see that reflected here. What do? If there's an a, you multiply every y value by a to get the point on the new graph, or at least to start getting it. Okay. B causes a horizontal stretch by a factor of 1 over b. Reminder that b 1 over b weirdness is just because in the equations x isn't isolated. So in our function notation, we can see it looks like we're multiplying by b, but remember, x is not isolated in the equation. If we were to isolate x to actually see what the effect of that b was, we would see that we ended up dividing the other side by b, right? So how did the x's change? Well, they were equal to stuff. They're going to end up being equal to stuff divided by b, okay? So that's why that 1 over b is there. And a horizontal reflection across the y-axis if b is negative. Again, that makes sense because we're just multiplying every x value by 1 over b. So if b is negative, we change the sign of those x values, reflecting them across the y-axis. Okay, and again, you can see that reflected here in the, maybe I shouldn't use the word reflected, but you can see that represented here in the mapping notation. If you have a point x, y, and there's a horizontal stretch occurring, what do you do to every x? Well, you multiply it by 1 over b. Okay, K is the vertical translation. So K causes a vertical translation, K units upward if K is positive, or downwards if K is negative. Again, that kind of makes sense because you can see, y used to just be equal to f of x. Now all this stuff is happening, and then we're adding K. We're adding K to every y value. So it's going to be K units higher. If K was positive, or if K is negative, it's now K units lower. Okay, again, look at that. there it is in the mapping notation, right? Yes, we multiply by a if there's a vertical stretch or a vertical reflection, but then we're adding k to every y value. And the effect of that is the graph just shifts upwards or downwards if k is negative, okay? H causes a horizontal translation, h units to the right if h is positive, or to the left if h is negative. And again, we see that here, that x minus h, okay? Reminding us there again, sometimes it looks a little weird because it's like x minus 3, but that means h is positive and it's actually shifting to the right by 3 units. Again, because x isn't isolated. If we wanted to isolate x to see what the effect was, we would end up adding 3 to both sides, and we would see that all x values have actually been increased by 3, moved to the right by 3. You can see that here in the mapping notation as well. Okay, so all we're going to do now, folks, is apply these with a little more, focus on radical functions. But it's all the same stuff from Unit 1. Literally nothing's changing here in the way we have to think about these. Okay, so we can apply all of these transformations to the graph of f of x equals root x. They work the exact same way and can have the exact same effects on our domains, our ranges, all that good stuff that we talked about in Unit 1. Now, again, the reason we're talking about this all over again, I mean, we're going to apply it to radical functions, so it's worth reminding ourselves anyway. But you're going to kind of see a theme, like I said here in Math 30-1. We can take this very basic radical function, y equals root x. We sometimes call this a base function or a parent function because we can actually use this with transformations to think of any radical function. We can pretty much think of the graph of any radical function, any one you could dream up, as being like y equals root x, just having been transformed in certain ways, okay? So you can take any radical function, y equals 3 root x minus 2 plus 6, and you can use that. You can say, okay, that's going to look a lot like this, but if we applied certain transformations to it. So this is kind of our base function for radical functions that we're going to think about as like a starting point often, and then think about, okay, so what would we have to do to that function to end up with the equation we have now? And we can think of that any radical function as y equals root x, but just having been transformed in certain ways. So you can see the potential here, right? It's like y equals a times the square root of b times x minus h plus k. Imagine the different number of radical functions that we're going to be able to deal with, right? If we're allowed to make a, b, h, k different things, and then we realize, oh, we can just think of those as transformations to this, that allows us to describe a lot of radical functions. There's a lot of different things we could put in there or think about having been put in there in order to think about a pretty complicated radical function as it relates to our base function y equals root x. I just want to make a little note on if you're wondering, hey, where did that come from? Where did we get this? That's not on my formula sheet. You're right, it's not on your formula sheet, but it doesn't really need to be because this is on your formula sheet, the general form of a transformation to a function in function notation, right? And all we're doing is applying that to this specific function. So again, these are in general. To transform any function f of x, you can, if you want to vertically stretch it, horizontally translate it, and vertically translate it, you can do these things, right? These are instructions. It says take the original f of x, instead of inputting x's, input b times x minus h, right? Essentially, find f of, instead of f of x, first replace x with b times x minus h. So let's just do that for our f of x equals root x. What's f of b times x minus h? Well, if we're trying to do this stuff and our f of x is root x, that just means we've got root b times x minus h. That doesn't look much like an h. There we go. Okay, so see what I mean? All we've done is apply these general instructions for transforming any f of x to this specific one that we're now thinking about, y equals root x, right? So again, f of bx minus h means replace x with bx minus h in the function you're trying to transform. There we go, I did it. It was root x, now it's root b times x minus h. Then what does it say to do with f of bx minus h? It says multiply it by a and add k. right? Multiply it by a and add k. So if we do that, I'm going to take root bx minus h and multiply it by a. And then I'm going to add k. And that's where this comes from. So this is like the general form, but it's specifically applied to y equals root x, which is kind of what we're trying to think about here now that we're moving into radical functions. Again, we're going to use y equals root x as kind of our reference, right? How is this more complicated radical function like y equals root x having been transformed? Okay, and so what that's going to allow us to do is let us write the equation for a radical function from its graph, right? If we're given a graph, we can say, okay, this kind of looks like y equals root x if you translated it this way and stretched it that way. So I can start writing the equation because I can think of what my h or my b might be, and that lets me start writing the equation, right? See what I mean? We can look at a graph and compare it to y equals root x, and that can let us say, all right, it's like y equals root x got messed with in these ways. And there we go, we're on our way to writing its equation. Or you can write its graph from its equation, right? Again, if you're given its equation, you can say, okay, I'll start by thinking about y equals root x, but maybe I see a 3 here, so I'll vertically stretch where y equals root x would be by 3. I'll multiply its normal y values by 3. And maybe h is 2. So I'll take those x values and I'll slide them to the right by 2, right? The equation basically tells you, hey, take y equals root x and transform it in these ways if we look at it in this context. Just don't forget RST, right? Reflections and stretches have to happen before translations because reflections and stretches involve multiplication. We're multiplying every y or every x by something. Translations involve addition or subtraction. And the order of operations dictates BEDMAS, right? Multiplications must come before additions or subtractions. So RST. So order of operations tells us we need to do stretches and reflections before we do any transformations. That shouldn't say transformations. That should say translations. Whoopsies. Translations. There we go. Okay, so since we're going to be thinking a lot about y equals root x, that's kind of our home base that we then think about transforming to make other radical functions, it's worth getting to know our home base pretty well, right? Let's think about this y equals root x here, so we can start thinking about transforming it, right? We got to know where we're starting from pretty well if we want to use it as a reference to transform other stuff. So what's the domain of this? Well, we kind of talked about it, right? I mean, two ways we can look at it. The graph shows us that x is always greater than or equal to 0. The equation also confirms that. We're taking the square root of x, so x needs to be greater than or equal to 0. Can't take the square root of a negative. So our domain is all x's such that x is greater than or equal to 0 and an element of the real numbers. Okay, the range, again, both the equation and the graph back us up here. If the smallest x can be a 0 and y is just the square root of x, well then y can be the square root of 0 as its minimum value. It's never going to be negative though, right? It can be as big as we want. X can become a billion and y gets really big too. It's the square root of a billion, right? But it never will go below 0. Y can never be below 0 because x can never be negative. So the range, the set of all y's such that y is greater than or equal to 0. And that's exactly what we see on our graph as well, right? Y never goes below 0, never dips down here. All right, endpoint. This is a terminology thing that we use for radical functions. It's shockingly, it's where the graph ends. It's the point where it ends. Mathematicians are so creative with their names sometimes. It's the point where it ends, so we called it the endpoint. Okay, now, what do I mean by ends? The graph keeps going forever this way, right? I mean, it's cut off, but technically there should be an arrow there, right? There's no reason we can't put bigger and bigger x's in and take the square roots of them. There's no reason we can't keep getting bigger and bigger y's out by putting bigger and bigger x's in to square root, okay? But there is a place where the graph just kind of ends at 0, 0, right? That's where the domain cuts off. We can't have negative x's, and so the graph just kind of comes to an abrupt stop there. So our endpoint is 0, 0. That's what we call it. The endpoint is going to be really helpful for us for thinking about these transformations because again, it starts from 0, 0, so where it ends up tells us a lot about the graph. More on that as we go. Some key points to use in transformations. Again, right, like we know the points that this should pass through, and if we ever forget, it's pretty quick to just say, let me put in some perfect squares here and figure out what y would be. Technically, we could put, any x's in, but the square root of a non-perfect square is kind of an ugly decimal, an irrational number, right? It's an irrational, non-repeating decimal. So make life easy for yourself. Pick some nice, easy points. Like let's say, 0, 0 is a really good one. That's our endpoint. 1, 1 is a really good one. How about 4, 2, right? Notice what I'm picking for my x's. I'm picking perfect squares because I know I'm taking the square root of x. So if I want nice integer numbers, I'll just pick perfect squares, and that will always give me nice integer points, right? Rather than doing like the square root of 5 and getting like 2.3674226, whatever it ends up being, right? Why bother with that when I could just make my x's perfect squares and figure out a nice integer y that goes with them, right? I mean, we could go on and on and on and on. 25, 5, 36, 6, 49, 7, yada, 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 right? Those are nice points we can use, okay? If you need a little reminder of how did I know the perfect squares so quickly, remember, they're just, 1 squared, 2 squared, 3 squared, 4 squared. Right? 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. So that's why I chose the perfect squares there, because I know we're taking the square root of x to get our y. I might as well pick nice perfect squares that'll give me nice integer y's out. Okay, let's try some stuff out, looking at some transformations of these radical functions. All right, so the graph of f of x equals root x is transformed into y equals g of x by reflecting it across the x-axis. So it's asking us, what is the equation of the transformed function of g of x? Well, okay, let's back up a sec. By reflecting it across the x-axis. So that's all we do. We reflect it across the x-axis. What does that tell me about? Which parameter? A, B, H, K? Tells me about A, right? We've reflected it across the x-axis. What does that mean for A? Means A is negative, and I mean, it didn't mention a stretch or anything, so A must just be -1. We've taken every y value and multiplied it by -1. That's going to change all of these positive y's into their, their negative twins. So we're going to end up seeing it reflected across the x-axis. So then it asks us, what is the equation of the transformed function? Now, again, for any square root, we kind of just proved, right? For any radical function, it's a times the square root of b times x minus h plus k. Well, in this case, our b, our h, and our k, they didn't say anything about horizontal translations or horizontal stretches or vertical translations. They just said it was reflected across the x-axis. So that tells us that h must just be 0. We're not translating it. Same goes for k. And then b must just be 1. We're not multiplying the x's by anything that's going to change them, right? B must just be 1. No horizontal stretch, no horizontal reflection. So applying that here, right, if we've got, since a is the only thing that actually has an effect, g of x equals a times f of x, right? And that's just also using, we can think of it in this specific radical form, but it's also just using the general form to transform any function. Take the original function, f of x, replace x with bx minus h, multiply by a, and add k, right? Well, in this case, h and k are 0, b is 1, so take the original function f of x, and all we've actually got to do is multiply it by a. So if f of x was root x, then g of x is a times root x, and a is just -1. So g of x equals negative root x. That is what the equation of the transformed function g of x must be. Now it wants us to sketch the graph of this transformed function, y equals g of x. So they were nice enough to give us the graph of y equals f of x, which is just root x, okay? Let's sketch the graph of negative root x. So again, let's just pick out some points, and what do we do with a negative a? What do we do with a in general? We multiply the y values by that a. In this case, our a is just -1. So I'm going to make my life a little bit easier. I'm going to pick points that are nice and easy, right? 0, 0. Well, hey, what's 0 times negative 1? It's still 0. Do you remember what we would call a point like 0, 0 for this transformation? We would call it invariant, right? It's not going to change because 0 times negative 1 is still 0. How about this one? 1, 1. Now that might change, right? We've got this point here. Actually, I'm just going to point out my points. I'm going to do 1, 1. Okay, so if I multiply all y values by negative 1, which is what an a of negative 1 tells us to do, that point's going to end up at 1, negative 1. Notice it's been reflected across the x-axis, right? It's equidistant to the x-axis as this one. All right, I'm going to cherry pick some nice points. How about 4, 2, right? There's 4, 2. We would expect that to be on the graph of y equals f of x because y equals square root of x because 2 is the square root of 4. Okay, so multiplying that y value, 2, by negative 1, we get 4, negative 2. So there's a point on g of x, which is just negative root x. Notice it checks out, right? The square root of 4 is 2, so the negative square root of 4 will be negative 2. Moving on here, you can probably guess what the next point I'm going to cherry pick is. How about 9, 3? Okay, multiply that y by negative 1, we get 9, negative 3. What do you think I'm going to do next? Yeah, 16, 4. That's a good point. Multiply that y value by negative 1, we get 16, negative 4 as the corresponding image point. Okay, and we can get a pretty good idea of the shape of our graph now, right? Looks something like this. I'm always bad at drawing the parabolas smoothly, but I did okay there, right? This would be y equals g of x, which was negative root x. Notice something kind of interesting here that we actually did encounter earlier in the course. Remember when we were taking the inverse of parabolas? Like if we had y equals x squared, we swapped x and y, and then we solve for y, we square rooted both sides. Since we're taking the square root, we have to remember that it could be plus or minus x equals y. And we ended up with something that looked a lot like this when we took the inverse of those parabolas. Notice this negative part, right, y equals negative root x, that's kind of the bottom part. This y equals positive root x, kind of that positive part. So it actually checks out. We've kind of seen this before, this y equals negative root x. It's kind of the bottom half when we take the inverse of a parabola, right? An inverse parabola, the inverse of x squared was plus or minus root x. Y equals plus or minus root x. We can kind of see how that gave us that parabola shape. Now, our transformed function is just this part. This is y equals negative root x. And you can tell we did it right. I mean, this looks like a reflection. The black looks like a reflection of the red across the x-axis. So there we go. We've transformed it. Now it wants us to state the domain and the range of the transformed function, y equals g of x. Well, I mean, again, we could look at the graph. We can see that the domain is still x must be greater than or equal to 0. But honestly, even without sketching the graph, if g of x equals negative root x, why do we have restrictions here in the first place? Because we can't take the square root of a negative, right? What are we taking the square root of? X. So what does that mean for the restrictions on x? X can't be negative. X must be greater than or equal to 0. So our domain would just be, like we saw on the graph, the set of all x's such that x is greater than or equal to 0. X is an element of the real numbers. Now for the range, again, the graph shows us, we can kind of see, looks like now y must be less than or equal to 0, but the equation can back us up here as well, right? If g of x equals negative root x, we know that x can be as low as 0, but no lower, right? It can never be negative. So the square root of x is always going to be something positive, right? I mean, that's true for any square root. You can't take a square root and get a negative answer. So if this is always going to be positive and there's a negative slapped in front of it, we're taking a positive and multiplying it by negative 1, that kind of indicates that, oh yeah, y is always going to have to be negative, right? If root x is always positive, then negative root x is always negative. It's a negative times a positive, no matter what x's we put in that we're allowed to put in. So we can see that our range will be all values of y such that y is less than or equal to 0. Just like our graph suggested. Cool. Okay, let's try another one. What is the new equation, domain, and range if y equals root x is reflected horizontally across the x-axis? Okay, so now we're doing a horizontal reflection. What does that tell us? A, B, H, or K? Tells us B, right? It tells us that B must be -1. Okay, so again, if we take our, y equals a root bx minus h plus k, which again, do you need to memorize that? No, not really, because it's just taking this, how to transform any function f of x, and applying it specifically to y equals root x, or f of x is root x, right? This is what you end up with when you do that. Replace x with bx minus h, multiply it by a, add k, okay? So again, no mention of a translation or a vertical stretch or a vertical reflection. So it seems like b is -1, h and k are 0, a is just 1. So that means y equals, a is 1, so the square root of -1x, right? We're going from y equals root x, and we're replacing, well, here, we're just going to go to y equals root bx, right? Y equals root x becomes y equals root bx. So y equals root -x if b is -1. There's the new equation. Okay? Now, it's asking us about the domain and the range, okay? We will graph it, but let's actually challenge ourselves here. Let's see if we can figure out the domain and the range before we graph it. That sounds kind of fun. So why would we have restrictions on our domain here? Well, because we're taking the square root of something. What can we not take the square root of? A negative. So right now we're taking the square root of -x. You might think, oh no, that's kind of by default negative, isn't it? Well, no, because what if x is negative? Then I have a negative, which would be a positive. So, don't panic. We know that we can't take the square root of a negative. We're taking the square root of -x. So -x must be greater than or equal to 0. Okay? A couple ways you could look at this. We could divide both sides by -1. Divide both sides by -1. That would give me x must be less than or equal to 0. If you're freaking out right now and saying, no, it's greater than, remember, whenever we divide both sides of an inequality by by a negative, we need to flip the inequality because we're changing both sides of the inequality, right? I mean, just for a quick example, if we change both sides, like let's say 7 and -4, right? 7 is greater than -4. But if I change the signs of both of them, so I make -4 +4, I make 7 -7, right? Well, 4 is greater than -7. So 7 was greater than -4, but -7 is less than +4, right? That's why when we divide both sides by a negative for an inequality, we're changing both signs on either side. So we're kind of flipping them across the number line and therefore reversing what the inequality was saying before. Okay? Another way you could get to the same thing is add x to both sides. You'd have 0 is greater than or equal to x, and therefore x is less than or equal to 0. But that's our new domain. So now our domain is the set of all x's such that x is less than or equal to 0. Which again, looking back at the equation, right? We don't have to be math robots. Let's look at the equation. Yeah, that makes sense. If x is always negative, then I have a negative, and I'm taking the square root of a positive, because a negative is a positive. So the only way to make this defined is to make sure that x is always negative. Can you kind of see how that makes sense if we're reflecting it horizontally? You can start to picture the graph after a horizontal reflection. Cool, right? Okay, now let's think about the range. The greatest in this case that x can ever be is 0, right? So y could be the square root of 0, but then as we start getting more and more negative x's, like y could be the square root of, 1, which is 1. Y could be the square root of 4, which is 2. The square root of 16, which is 4. Notice y is just going up and up. So once again, our range is just going to be, in this case, y will be greater than or equal to 0. Right? Sure, if x is 0, y is 0, but as we get bigger and bigger negative x's, we're just taking the square root of a bigger and bigger number, and therefore y comes out as being a bigger and bigger number. All right, let's try actually reflecting this and drawing the graph. We challenged ourselves successfully. We got the domain, the range, and the new equation. Let's draw the new graph. So again, let's cherry pick some points. I'm going to cherry pick the same ones. How about 0, 0? How about 1, 1? How about 4, 2? How about 9, 3? And 16, 4? Okay, now what does it actually mean we're going to do to every x if b is negative 1? Well, we multiply every x value on the original graph by 1 over b. Well, 1 over negative 1 is still just negative 1, so we're multiplying every x by negative 1, and that's going to cause the sign of each x to change, and therefore these positive x's are going to become their negative twin versions. So multiplying the x value here, 0, 0, multiply 0 by negative 1, you still get 0. Hey, invariant point. Okay, 1, 1, if I multiply the x value by negative 1, I get negative 1, 1. 4, 2, I'm going to get negative 4, 2 when I multiply the x value by negative 1. 9, 3, I'm going to get negative 9, 3. And 16, 4, I'm going to get negative 16, 4. So we can see it kind of, oh boy, jumped all the way up to the top of the notes. I'm bad at drawing these. I'll do my best. Better on paper. It's hard to do it on the iPad. Something like, oh boy, something like that. Okay, that's not terrible. That's pretty good. Okay, there we go. And, you know, we can check our work just by one of the best ways to check your work sometimes is, does that look right? Does that look like a horizontal reflection across the y-axis? And I think it does, right? Every point has one that's equidistant from the y-axis, sorry, like the y-axis is a mirror. And more than anything, it kind of does look like we just took this red one and flipped it across the y-axis. So I'd say we did a pretty good job there of reflecting y equals root x horizontally across the y-axis. All right. Now in number 3 here, they're giving us the equation. So for y minus 3 equals root 2x minus 1, they want to know, describe how this graph could be obtained by transforming the graph of y equals root x. Like we learned in, Unit 1, this is often, first to start thinking about that, it's really nice to just figure out, okay, what are A, B, H, and K? Because those tell you the vertical stretch or reflection, the horizontal stretch or reflection, the horizontal translation, the vertical translation, right? So let's just think about this. We know that it's y equals, specifically for a root function, if we're transforming specifically root x, it's a times the square root of b times x minus h plus k, right? And see the power of this, because this is just the equation of some radical function, right? It's not saying, hey, you're going to transform y equals root x, but we can use this fact to now compare it to this and think, well, this graph, whatever this radical function is, it's going to look like y equals root x if we did mess with y equals root x in some ways, right? By taking that base graph y equals root x and stretching it or translating it or reflecting it, you can make it look like any radical function. And that's the power of kind of going at it this way, by taking our base function, our very simple y equals root x, and imagining messing around with it in order to get, some new equation. All right, so with that in mind, let's take a look at our equation and say, okay, this is like y equals root x if y equals root x was given an a of blank, a b of blank, an h of blank, and a k of blank, okay? So first things first, I notice they're trying to trick us. They wrote it in the y minus 3 way. Let's first move that 3 over so that we really do have something that looks like this, okay? Looks like our general notation for transforming a radical. Okay, how would I do that? I'd add 3 to both sides. So y is going to equal the square root of 2 times x minus 1 plus 3. And now we can pick out a pretty easily, right? A, b, h, and k, pretty easily. So what's a? Maybe I should pull this over here so we can compare a little more directly. I don't know why I drew it all the way over there. There we go. Okay, so what is in A's spot? Oh boy, now it's a little crowded. Quickly rewrite that. Y equals root 2x minus 1 plus 3. There we go. Okay, so what's in A's spot? Well, I mean, nothing, but shouldn't say nothing. It's a 1, right? A is 1. So what's that going to do? It's going to multiply every y value by 1. In other words, it's not going to change it. In other words, there's no vertical stretch or reflection. What about B? I do see a B. Looks like B is 2. So we'll keep that in mind when it comes time to describe the transformations. What about H? Compare. Looks like H is 1, positive 1, right? Because it's x minus H. So H is positive 1. And finally, do we see a K here? Yeah, looks like K is 3. Okay, again, right? Makes sense. Y, if we're thinking about it as it compares to y equals root x, used to just be equal to root x. Now it's root this stuff, but we've added 3 to every y value. Well, that's going to shift every y value up, vertically translate it up by 3. Okay, so what are the associated transformations? Let's remember to do our RST. Okay, don't forget reflections and stretches before translations. Okay, so don't need to worry about any vertical stretches or reflections, but we do need to say that there's been a horizontal stretch by a factor of, now careful, is it 2? No, it's 1 over 2 about the x-axis. Nope, not about the x-axis, about the y-axis. That's where we stretch from for a horizontal stretch. Again, because we're going to stretch stuff about the y-axis horizontally. Maybe away, maybe towards, but that's kind of our base point that we're stretching from. Okay. Now, H is, okay, we've done our stretches. I don't see any other stretches to talk about, so I'm going to say then, because order is important. We want to be clear with our answer that we understand we have to do the horizontal stretch first. Then we could do a horizontal translation, 1 unit, left or right? To the right. Good, because H is positive 1. Finally, a vertical translation, 3 units up, because K is positive 3. Okay, so it wants us to represent the transformation in mapping notation. Well, again, we now know our B is 2, our H is 1, and our K is 3. And remember, mapping notation just provides more specific instructions on how to individually describe a point, right? This is showing us how the overall equation turns out, but if you just have one point x, y that is on this graph of y equals root x, what are you going to have to do to that point and to every point x, y to get the graph of the new function? Well, you're going to multiply the x's by 1 over b, and you're going to add h. Right? If h is negative, that means you move it to the left. You're adding a negative. If h is positive, that means you're moving it to the right. You're adding a positive. So plus h. And what are you going to do to each y? I mean, you're going to multiply them in general. We can just do it in general here. We know our a is 1. But in general, you multiply every y by a, the vertical stretch or reflection, and then you add k. So what does that mean for this one? Let's get more specific now. We're going to take our original function, points on our original function, y equals root x, and what are we going to do to them? Well, our b is 2, so we're going to multiply them all by 1 over 2, 1/2. In other words, divide them all by 2, and then we're going to add 1 to all of them, because that's our h. So a point that was at x, some x, is now going to be at that x times 1/2 plus 1. What about the y's? Well, our a is 1, so I'll just leave it out here, but our k is 3. So whatever y it was at before, it's now going to be at y plus 3. If it was at 0, now it's at a y of 3. Okay, and there we go. And now it's saying use your mapping notation with some points to help sketch the graph, right? We can always do this. Sometimes students will say to me, I don't know how I'm supposed to go about transforming this, right? Well, you know what you're doing to each point individually, so pick some points that are on the original graph and do that to them. That will give you new points, okay? So let's do it. Now again, you probably think, what points am I about to use? I'm gonna make my life easy. I don't wanna use some, random kind of decimal irrational numbers. I'm gonna use nice integer numbers. I'm gonna use the points on y equals root x, where x is a perfect square. So 0, 0 is always a nice one. 1, 1 is always a nice one. How about 4, 2? 4 is a perfect square, so the square root of 4 is 2. What's my graph go up to? Okay, I'll do 9, 3. That's gonna give me 4 points. That's going to give me a pretty solid idea of the shape of this probably. So 0, 0. If I take 0, 0 and I apply these transformations to it, so I do it 1/2 times x, so 1/2 times 0 plus 1. That will be where that point ends up. We'll figure out what it is in a second. And then I'm going to take my y, so for this point, 0, and I'm going to add k. So for this transformation, 3. So in other words, it's going to become, well, half of 0 is 0, plus 1 is 1. So the new point will be at 1, and then 0 plus 3 is 3. So there's a point on our new graph. The point that was at 0, 0 will now be at 1, 3. So let me add that point. 1, 3. Okay, repeat for 1, 1. I'm going to multiply 1 by 1/2 and add 1. Okay, so I'm just going to drop the color coding in the interest of time here. 1/2 of 1 plus 1. I'm going to take the y value and I'm going to add 3. So 1 plus 3. So that point that on y equals root x, it's at 1, 1. On our new graph, or our transformed function, or our function that we're thinking about as a transformation to y equals root x, it's going to end up at, okay, half of 1 is, I'm going to call it 0.5. I mean, it's 1/2, but I'm going to say 0.5. Just seems a little easier to think about on the graph. So 0.5 plus 1 is 1.5, and then 1 plus 3 is 4. So there's another point that we can put on our graph, 1.5, 4. So there's 1. 1.5 would be halfway to 2 from there, and then 4. 1.5, 4 is another point. And I was going to keep doing this. So 4 times 1/2 is 2. 2 plus 1 is 3. So this point's going to end up with an x coordinate, showing a little less work here, I know, but right, I'm just doing the same thing. Multiply x by 1/2, add 1. 4 times 1/2 is 2, plus 1 is 3. And then I'm going to add 3 to the y, so 2 plus 3 is 5. So 3, 5 is a point on our graph. So x 1, 2, 3, y 1, 2, 3, 4, 5. That point should be on our graph. And we can see it kind of has that characteristic radical function shape showing up now, right? That kind of bend, but the bend gets less and less dramatic as x increases. It's kind of what we see here as well. Okay, last one, 9, 3. Where's that going to end up? I'm going to multiply 9 by 1/2, so 4.5, plus 1 is 5.5. Just doing the mapping, and then I'm going to add 3 to the y value, so 3 plus 3 is 6. So 5.5, 6. Well, here's 5, there's 6, so there's 5.5. And then on the y-axis, 6. So right around there, 5.5, 6. And there we go. We've got a pretty good idea of the shape from here. I mean, I guess we could kind of do a couple more if we wanted, but it's going to roughly have this shape. Okay, maybe I actually will do one more. Let's do 16/4. 16/4 is going to become, half of 16 is 8. 8 plus 1 is 9. 4 plus 3 is 7. 9, 7. There we go. That'll give us 9, 7. So our graph's going to end up looking something like that. We've sketched the graph of y equals root 2 x minus 1 plus 3. Now, isn't that cool, folks, right? This is just some radical function, a like semi-complicated radical function. And we were able to sketch its graph by thinking about, okay, but how is this kind of like root x, but having been messed with in certain ways? How is it like taking root x and doing something to every point x, y? And that allowed us to graph this thing by thinking about how it's kind of like root x, but having been transformed. Isn't that cool? All right, state the domain and the range. I mean, from the graph, let's just use the graph here. What's our domain? Looks like x is always greater than or equal to 1, right? That's the lowest value of x that we see. So our domain, the set of all x's such that x is greater than or equal to 1, x is an element of the reals. Our range, well, again, we can see on the graph, it's the set of all y's such that y is greater than or equal to, nope, not 1, 3. Right? That's the lowest y ever gets. It never goes below 3. It does get to 3, but it never goes lower than 3, and then it just goes up from there as x increases. Could we have gotten this from the equation? Absolutely, right? We were taking the square root of 2 times x minus 1 from the equation, right? Y equals root 2 times x minus 1 plus 3. So we're taking the square root of 2 times x minus 1, so that can't be negative. So just divide both sides by 2 to see that x minus 1 must be greater than or equal to 0, and then add 1 to both sides. Sure enough, x must be greater than or equal to 1, just like our graph suggested. Okay. Similarly, for our y here, right? Well, you can see, like, we could make this 0. That's the smallest we could get there. We could get the square root of 0, right? For example, if I made x 1, like we see here, when x is 1, I have the square root of 2 times 0, so the square root of 0, so 0, plus 3. So the lowest y can ever get is 3, right? If I make x 1, then I have the square root of 0, which is just 0, plus 3. So when x is 1, y just ends up being 3. From there, as x gets larger, y just gets bigger and bigger. So we see that coming out there as well. So that confirms that our range would be all y's such that y is greater than or equal to 3, like our graph showed us. Okay, so now is a good time to pause the video, try out at least this practice question, but again, if you're liking to kind of mix some sections of practice in while you're learning the lesson, you could do more, of course, right? But at least try this one while it's fresh in your brain. Page 72, number 2A. If you try B, C, D, you'll see more similar examples, okay? But asking how to transform the graph of y equals root x into the graph of y equals 7 root x minus 9, and also state the domain and range. So go ahead, give that one a shot, and when you're finished, we'll move on to determining the equations when given the graphs. So flipping this around, instead of going from equation to graph, how do we go from graph to equation? All right, so in order to do that, to get the equation from the graph, again, we're going to apply the same thought processes we would have applied back in Unit 1, right? It's just now we're being more specific to radical functions. And so the nice thing is we can just think about y equals root x and compare. If we're given some graph and it doesn't look like y equals root x, we can kind of think, well, how would we have turned how would we have turned y equals root x into what we're seeing here? What would we have to do? Would we have to translate? Would we have to reflect? Would we have to stretch, right? By working that out, what you're really working out is a, b, h, and k. And if you can work out a, b, h, and k, you can write the equation of the function in this form. Okay, so by comparing to what we know the graph of y equals root x looks like, we can figure out what a, b, h, and k need to be, and then use them to write the equation for any radical function, right? That is the equation of a radical function. So how do you go about that? I mean, same thought processes, same kind of ideas that you would have applied back in Unit 1, like I said. Typically, first, we're going to check for any stretches, because before we can start thinking, I mean, that's actually not entirely true, but often stretches are a good place to start, just so you kind of know what you're working with in terms of stretches. Okay, how do you know? I like to use kind of like the width and the height from the end point to the quote-unquote first point. Let's call it the first point, meaning from that 0, 0 to that 1, 1 that should be on y equals root x. How has that changed? Okay, so that's a good way to identify a stretch. So you know that on the graph y equals root x, if we start at the endpoint and move 1 to the right and 1 up, we should reach another point on the graph, 1, 1, right? We should go starting from the endpoint here, 0, 0, we should go over 1, up 1. Now imagine horizontally stretching this graph or vertically stretching this graph. Can you see how those would change, right? That's that comparison. We're going to look at how has that changed, and that can tell us about a vertical and or a horizontal stretch that might have occurred. Basically, from the endpoint to the first point should have like a width of 1 and a height of 1. So comparing the width and height of this on the graph you're dealing with could tell you the vertical stretch, and therefore A, and or the horizontal stretch, and therefore 1 over B. So for example, if we had, a width of 1 but a height of 2, that suggests a vertical stretch by a factor of 2. So our A is 2, right? If we see, on our graph now, starting from the endpoint, we go over 1, but we have to go up. That's not drawn very well. Over 1, but we have to go up 2 to get to another point on our graph. Right? Well, that suggests this graph is now twice as tall, so to speak, as it used to be. Right? Used to be if we go from the endpoint, we go over 1, up 1. Now if we go over 1, we have to go up 2. So it suggests it's been vertically stretched by a factor of 2. Or what about a width of 4 but a height of 1? That suggests a horizontal stretch by a factor of 4, right? So if instead of that you've got something like this, where now starting from the endpoint, if you move over 4, you have to go, instead of just going over 1, you have to go over 4 until going up 1 gets you back to that point on your graph, right? This has been horizontally stretched by a factor of 4. Okay, it's 4 wide, 1 high. On an unstretched y equals root x, it's 1 wide, 1 high from the end point to that kind of first point. Now, this is a great strategy, but you can also algebraically determine A after you've determined your h and k using any other point you can see on the graph as y and x, like we would have done, like we did with polynomial functions and stuff like that. If you've got everything in the equation except for A, well then pick a point, make that your x and y, and then the only thing you don't know in the equation is A, so you can solve for it, okay? Next up, check for any reflections. You might be able to figure out, okay, it's been stretched because the width and the height thing we were just talking about. Reflections are pretty easy to spot because, again, you know what y equals root x should look like, okay? You know that y equals root x has an endpoint at 0, 0 and extends up and to the right in quadrant 1, right? In other words, it looks like this. Do it in red so it stands out. That's what y equals root x normally does, right? As x gets bigger, so does y, proportional to the square root of x. So the direction that your graph extends to can tell you about reflections that occurred and therefore the signs on A and B. So you can get the size of A and B from looking at the stretch, comparing the widths and the heights, so to speak. But we can get the sign on A and B by seeing if a reflection has occurred. So for example, if it extends downwards instead of upwards, it's been reflected in the x-axis. So A would be negative, right? That just means if instead of doing what we just drew for y equals root x, what if it does this? We saw that earlier in that example. If it extends downwards towards y is negative infinity, it must have been reflected in the x-axis, got flipped upside down, so to speak. If it extends to the left instead of to the right, it must have been reflected in the y-axis, so our b is negative, right? That would look like this. Instead of extending to the left, where x gets more and more positive, sorry, to the right, where x gets more and more positive, it extends to the left, where x gets more and more negative. It has to have been reflected across the y-axis, right? Just like we see here. If I reflected this across the y-axis, it would end up looking like this. Instead of extending to the right for x's, it extends to the left. Maybe both happened. Maybe both a vertical and a horizontal reflection occurred, So instead of extending up, it extends down, and instead of extending right, it extends left. So that's going to do something like this, right? There's both a horizontal and a vertical reflection, right? Reflected across the y-axis, then reflected across the x-axis, you end up with something like this, okay? Now, the end point is your best friend when it comes time to determine, has this thing been horizontally translated or vertically translated? It actually requires very little brain power to figure out, because let's walk this through and see why this makes sense. We know that y equals root x has an endpoint at 0, 0, right? The square root of 0 is 0, and x can't get any smaller than 0, so our graph just ends up ending there, okay? This can only be changed by translations, by sliding, right? That makes sense when you think about it. Stretches and reflections will never affect this point. Why? Because stretches and reflections involve multiplying this by 1 over b or this by a, right? But it doesn't matter what 1 over b or a are. 0 times anything is still 0. 0 times anything is still 0. So that endpoint on y equals root x is invariant to any type of stretch or reflection. 0 times 1 over b is 0. 0 times a is still 0. So that endpoint should never move because of just a stretch or a reflection. Meaning that if it did move, it was because of a translation. The only way to move those is to slide the graph, not to stretch or reflect it. So translating the graph horizontally, what's that going to change? If I slide something horizontally, I change the x value, right? So starting from 0, the x value gets shifted h units to the left or to the right. So it started from 0. So wherever it ends up, that must just be h, right? If it starts at 0 and now it's at -2, well, it got shifted 2 to the left. H is -2. If it started at 0 and now it's at +20, well, it got shifted 20 to the right. So h is +20, right? So directly, the coordinates of the endpoint, the x-coordinate, directly tells you the h value. Same goes for vertical, but with the k value and the y-coordinate of the endpoint, right? If I shift it, it's starting from y equals 0. If I shift it up 2 units, well, now my endpoint will have a y-coordinate of 2. So if k is 2, y will be 2 at my endpoint. If I shift it down 5 units, starting from 0, it's going to end up at -5. So if the y value of the endpoint is at -5, k must be -5. And there we go. That tells us h and k. So that's a super quick way to find h and k. And then we can think a little bit about the a and the b values by comparing to y equals root x. Let's go ahead and see if we can apply this here for some stretches to start out. So specifically it says determine the stretches that could be applied to y equals root x to obtain these graphs. We can actually tell, the question suggests it, but we can also see no translations occurred. The endpoint stayed at 0, 0. No matter what, if we had slid this around, that shouldn't be at 0, 0 anymore, okay? So let's take a look here. How could we have stretched this? How could we have stretched y equals root x to obtain this graph? Well, this is where I was referring to. We can kind of make use of that width height kind of test, so to speak, right? So starting from the end point, we can kind of see, like, if I go over 1, I could go up 2, right? Over 1, up 2. Is that what we would normally expect for y equals root x? No, right? Y equals root x, we should see endpoint at 0, 0, and then another point at 1, 1. So we kind of expect from that endpoint to the, first point, I'll call it, should have a width and a height of 1, 1. But this doesn't. This is higher, right? It's been vertically stretched by what factor? Vertically stretched by a factor of 2, right? So normally, right, or at least on y equals root x, this would be, 1, 1. But now, at that same kind of change in x, we're getting a y value that's twice as large. Its y values are twice as large. Well, there you go. If the y values are twice as large, what have we done to every y value? We've multiplied them by 2. So what does that mean? What transformation have we performed? What transformation involves multiplying every y value by 2? A vertical stretch by a factor of 2, right? So a equals 2, right? We've got a vertical stretch by a factor of 2 about the x-axis. Whoops, that A is not really part of my answer. Okay, now this one's interesting. It says for this one, see if you can approach it in 2 different ways. Are those 2 different ways equivalent? Okay, let's see. Well, we've got, right, I do kind of see 2 ways we could look at this. Again, we're kind of comparing to this, right, what we know y equals root x would normally have for its width and its height here. So we know when we go over 1, we should go up 1. Well, if I look here, going over 1, whoops, maybe I'll color code this a bit, going over 1, actually, use red, over 1, and then up 1. Sorry, going over 1, I don't actually have to go up 1 to get to my next point. I only go up 0.5 or 1/2, right? So we could think of this as a vertical stretch, right? Normally, y equals root x, we would have, we've now got 1, 0.5 as compared to, on y equals root x, that should just be 1, 1. So the y values are half as big. We've vertically stretched, we've multiplied every y value by 0.5 or 1/2. So this suggests a vertical stretch by a factor of 1/2. About the x-axis, I should really say. But I actually notice another way we could approach this. Because look, we also know, I mean, you could say over 1, up 1, but you could just as easily say up 1, over 1. But that's not what's happening here. We go over 4 and we go up 1. So we're going, look, this is 4 and 1. So compare that. 4, 1, as it compares to the normal y equals root x, which is just 1, 1. Width of 1, height of 1. This has a width of 4. So what does that suggest? It suggests a horizontal stretch, right? This thing is wider. It's been horizontally stretched by a factor of 4. So how can this be? How can we have 2 different things and both of them kind of make sense and they fit the graph? Well, these are actually equivalent. They're not different. Vertically stretching by a factor of 1/2 ends up being the same thing as horizontally stretching by a factor of 4 for these radical graphs. We've actually seen this. We saw it with parabolas, right? Again, you can kind of think of it like pizza dough. You could vertically stretch it by a factor of 1/2. In other words, make it shorter. So if you took Play-Doh, let's say, and you squished it downwards, imagine doing that with your hands. Well, what happens to it sideways? It gets thicker, right? It gets stretched horizontally, it gets wider when you vertically compress it down. And same thing, if you horizontally stretch it out, take the dough and horizontally stretch it out, vertically it gets shorter. The Play-Doh gets kind of thinner vertically in the middle, okay? We can prove this mathematically as well. Let's see. Are these ideas really the same thing? So if I take y equals, and I think of it as an A, as a vertical stretch, y equals a root x. Well, that means my equation here would be y equals 1/2 root x. Okay, y equals 1/2 root x. Whoops, I don't know why I'm putting a box around that. It's not part of my answer, but it is something I want to think about here. Versus thinking of it as a horizontal stretch. So y equals root bx. Replace x with bx to do a horizontal stretch. Well, if the horizontal stretch is 4, then b is 1 over 4. So look at this. My two equations, I've got y equals 1/2 times the square root of x versus the square root of 1/4 x. But hang on a sec, what's the square root of 1/4? To really emphasize this, I could split this up just to make it a little more obvious. This is the same as root 1/4 times root x. Root 1 is 1, root 4 is 2. So, oh my goodness, this is just 1/2 root x. Look at that. It's actually the same radical function. So we can think of it as a vertical stretch by a factor of 1/2. We can think of it as a horizontal stretch by a factor of 4. They end up being equivalent in terms of what ends up like actually, the equation of our function. So vertically stretching root x by a factor of 1/2 produces the exact same graph as horizontally stretching it by a factor of 4. And we can prove that by showing that it results in equivalent equations. Okay, so yes, I mean, they are equivalent. It asked, are they equivalent? Yes, they're equivalent. The vertical stretch by a factor of 1/2 is doing the same thing to the graph overall as a horizontal stretch by a factor of 4. This could actually be true for every radical function. Why didn't we do it for this one? I mean, there was just an easy, obvious answer here, right? You could say, oh, you could horizontally stretch it by, because you went up 1 and you went over, because what is that? How far are we going over? 0.2, 0.3? Right? So in this one, there was a pretty clear and obvious way to do it both ways, but this is kind of always true for these radical functions. So don't panic or anything. You'll be it's not like they'll ever try to trick you too much, but you might sometimes see it like this in blue, and maybe the answer key sees it in red. So if you do, don't panic too much. Ask yourself, okay, wait, are these really equivalent? Did we just kind of see these in two different ways? Because it's totally possible, right? This is a lot like what we saw with parabolas, like I mentioned. You could take y equals x squared, and you could vertically stretch it by a factor of 4 to get y equals 4x squared. Or you could horizontally stretch it by a factor of 2. Well, sorry, 1 over 2. So b is 2. Right? Replace x with 2x. And that gives you y equals 4x squared. Equivalent things, right? Equivalent equations. It's actually the same function in the end. If you take x squared and vertically stretch it by a factor of 4, you end up with the same graph and the same function as if you horizontally stretch it by a factor of 1/2. Pizza dough, right? You can stretch it vertically, that makes it skinnier horizontally, or you can squish it vertically and that makes it fatter horizontally, or vice versa. Okay, let's take a look and visualize this here on a graph just so we can, really drive it home. Again, I'm going to use Desmos here. I encourage you to use your calculator. Get comfortable with graphing stuff on your calculator. But Desmos allows me to do these sliders and these colors and stuff, which is nice for visualizing. So I've got y equals root x there in black. I'm going to add y equals a root x and y equals root bx in red and blue, respectively. Okay, they look the same as y equals root x right now because they are. I have a and b just set to be 1. So right now they're just y equals root x. But let's explore this idea of vertically and horizontally stretching it and how that can end up with the same results if we have the right vertical stretch and horizontal stretch, okay? So I'm going to move around a, right? I can vertically stretch it by messing with the value of a. Okay, let's do what we had in that example. Let's make a be 0.5, right? So it's shorter, like we would expect. Every y value has been multiplied by 0.5. I can also horizontally stretch it, right? I can horizontally stretch it, make b wider or narrower, so to speak. Let's make b what it was in that example. It was 1 over 4, right? It was 1 over 4. Whoops, I set this incorrectly. 1 over 4. There we go. Okay. In other words, 0.25, and look at that, right? It ends up being the exact same as our vertical stretch by a factor of 0.5. So we can achieve the same result as a vertical stretch with a horizontal stretch for these radical functions if we think about the horizontal and vertical stretches correctly, right? Again, we could go over 0.5, over 1 up 0.5, that's that point right there. Or we could think of it as now we're going over 4 up 1, so it's 4 times wider. Horizontal stretch by a factor of 4. Cool. All right, now let's see if we can put this all together and actually fully write the equation of a radical function given just its graph. Okay, so let's start out with a here. We're going to do it again by comparing to what y equals root x would look like, and then see how that tells us what this equation must be like. It's like y equals root x with these changes having been made. Okay, so I'm going to check for stretches first. Again, not necessarily doesn't have to be your first step, but I'm going to do it here because I noticed something right away. Look, here's my end point. Okay, my end point is right there. Now, normally on y equals root x, don't forget, we go over 1, up 1, and we should be back on the graph, right? Here, that's not the case. I could say, go over 1, up, but then it's some decimal. So we don't know what that decimal is. We're not going to do that, right? But notice here, to go up 1, I'm having to go over 2. So I go over 2, up 1. Now, what does that suggest? That suggests a horizontal stretch by a factor of 2, right? Every x value has been multiplied by 2. So that means b must be 1 over 2. And look at that. We're just picking away at this thing. Now we've got b. All that's left is a, h, and k. Now, often for these, when we pick a b, we no longer need to pick an h, right? Like we saw, it's just been horizontally stretched by a factor of 2. No vertical stretch needs to be involved now. Okay, we can often describe the horizontal stretch with a vertical or a vertical with a horizontal, but once we've got one, we don't really need to use the other now. Okay, horizontal stretch by a factor of 2, so b is 1/2. That actually means all we need to figure out is h and k. Well, remember, how can we do that? It's actually pretty quick and straightforward. We just need to look at the end point, because again, where is the end point for y equals root x? It's at 0, 0. So that wouldn't have changed from just this horizontal stretch. It would still be at 0, 0. 0 times 1/2, still 0. Okay, we know there's no vertical stretch anyway, but even if there was, 0 times a, still 0. Okay, or at least I shouldn't say there's no vertical stretch, but we don't need a vertical stretch to describe the equation of this graph. So the only way to have moved it is to have translated it. So we must have translated it horizontally. We went 3 units left, right? HT horizontal translation, 3 units left. And then we went 1 unit down. Vertical translation, 1 unit down, right? Our endpoint here ended up at -3, 2. Sorry, I don't know where I got 2 from. -3, -1. That is our h and our k, right? The only way to do that is with a vertical translation of -1, 1 unit down, I should say, and a horizontal translation of 3 units left. Okay, that's the only way to move it. Stretches and reflections aren't going to change it. You got to slide it 3 over, 1 down to move it from 0, 0 to -3, -1. So we've established that our h is -3 and our k is -1. So we got them all, right? K we know, h we know, and we know we don't really need an a here to describe it. Could we come up with an a? Sure, but we've got a b that does the trick, so we'll just go with that. So the equation is going to be y equals, we're going to let a just be 1, so square root of b. Now b is 1/2, since the horizontal stretch was by a factor of 2, x minus h. Our h is -3, so x plus 3. minus negative 3 gives us a plus 3, plus k, but k is negative 1. So plus negative 1 is just minus 1. And there we go. That's the equation for that radical function, right? Wasn't too bad. We just had to look at this graph and think about how is this like root x but having been changed in a few ways, right? That's the power of having this base function and understanding how we can take any base function and transform it to a more complex version of the same type of function. Cool, huh? Let's try this one. Okay. Let's look for stretches. Again, that doesn't necessarily have to be step 1, but just taking a look here. Endpoint is right here. This actually doesn't look like it's been vertically stretched or horizontally stretched, right? Over 1, up 1. Over 1, up 1. So our A and our B are not causing it to be stretched. However, I don't know if I'd go as far as to say A and B are both 1. Because do you notice something else that's happened here? How should a graph normally extend? How does y equals root x? What's its end behavior? Right? It should extend up and to the right, right? For y equals root x, we see it do this. As x gets larger, y gets larger, proportional to the square root of x. But this one is extending to the left. So what would have needed to happen to flip it like that? A reflection. A reflection in which axis? In the y-axis, right? It's been flipped sideways, horizontally. So this suggests that there's been a horizontal reflection across the y-axis. Horizontal reflection across y-axis, meaning that, what do we know about A, B, H, or K? We know that B is negative 1. Very good. All right, so we got B. We can see there's no A. We just need H and K. Well, that's pretty quick. We just need the endpoint. Again, starting from 0, 0, how do you get to, where's this? It's at 2, 4. How do you do that? Well, the only way is with a horizontal translation 2 units right and a vertical translation 4 units up, right? Stretches are not going to change the point 0, 0. Only translations can do that. So our endpoint is at 2, 4. That means we had a horizontal translation 2 units right. So H is positive 2. And a vertical translation, 4 units up. So our K is positive 2, right? Okay, probably should show a little more work and thinking there, but since we're kind of just talking through it together, if this were like a diploma, you'd want to explain yourself a bit more there, right? Not an essay or anything, but explain how you know that the endpoint could only be moved by a translation, okay, and how you know those must be the translations then, because it would start from 0, 0 on y equals root x, that kind of stuff. But that means we're ready to write it. So y equals square root b, our b is negative 1. I'm just going to write it as negative because the 1's not going to change anything. So negative x minus h, h is 2, so x minus 2, plus k, and k is positive 2, so plus 2. Oops, I don't know why I keep making k 2. Sorry, folks. You're probably screaming at your computer there. K is 4. K is 4 plus 4. There we go. Sorry about that. All right, and we did it. We wrote the equation from just the graph by thinking about how you could change y equals root x into this with certain transformations. And that's the equation we come up with. Cool, right? If you plug that into your calculator, if you graph this, it will just produce this graph, right? Same thing here. If you graph this in your calculator, it will just produce this graph. All right, now's a good time to pause, practice this skill a little bit of going from a graph to an equation. Okay, so do at least this one practice question while it's fresh in your brain. Feel free to take a little bit of a longer pause and try a few more and really solidify those skills, but at least try this one. And then when you come back, we'll talk about the last thing for this lesson, which is the square root of a function. All right, so what is the square root of a function? Well, are you ready to have your mind blown? It's when we take the square root of a function. Okay, so just like we can add, subtract, multiply, or divide functions, just like we did in Unit 1, we did all of those operations with functions, right? Added them together, subtracted them, divided them, all of that fun stuff. We can also take the square root of a function. We literally take the square root of the function's equation, and that's what we're doing. We're square rooting a function. So just like in that first unit, we can perform the operations on the equation itself, or we could perform the operation on individual outputs of the function, right? The y values, because f of x, right? Y is f of x. The value of the function is just what y is at a given x input. So we're going to do the same thing here. Remember, we're taking the square root of the function. So we still input x's, but the resulting outputs are going to be affected by the fact that the function now involves square rooting. Okay, so in other words, when we transform y equals f of x into y equals the square root of f of x, the x values on the original function stay the same, right? We're not changing what we can input, but we are changing what's going to come out as a result because of the fact that now we're square rooting. The y value becomes the square root of the original y value. So if we have a point on our original function, xy, and we take the square root of that function, the new corresponding image point will be at x root y. Okay, just to show you what I mean, right? Like, let's just do an example. If I have y equals, I don't know, how about 2x? If I take, actually, let's just be a little more clear there. If I have f of x equals 2x, if I take the square root of this function, so the square root of f of x, it's the square root of 2x. I just take the square root of the function. So that is the square root of this function here, y equals root 2x. Now notice, does this change what I can put in for x? I mean, it actually does. It is going to affect the domain of this. We'll see why. But I can still, like, I could put in 1, I could put in 2. We input the x's. So we're inputting the x's. The fact that they're being square rooted doesn't change that we're still just inputting certain x's. What it does change is what's y is going to end up being, right? If I put a 2 in here, then y is going to be 4. 2 times 2 is 4. If I put a 2 in here, I still put in a 2, so x is still 2, but it's the square root of 2 times 2, which is 4. So now it's the square root of 4, which is 2, right? Before, when x was 2, y was just 4. Now when x is 2, y is 2. So we went from a point 2, 4 to a point 2, 2. Notice x, y has become x root y. 2, 4 has become 2, 2. So that's why our x's still stay the same, because we're still just inputting the x's that we're able to. The y's that come out get changed because we're square rooting the entire function, and therefore its outputs. Okay, let's talk quickly about invariant points here, because we are kind of doing a transformation or an operation to a function, and some points might not change. Invariant points are just points that are unchanged by a transformation. When we take the square root of a function, those are going to be the points, if we think about it, right? We're going from xy to x root y. So what would need to be true about x root y for it to be the same as xy? Well, y would need to be the same thing as root y, right? That's the only way, where xy is the same thing as x root y. In other words, wherever the y value is just equal to its own square root. So are there numbers like that? Because it's asking us here, knowing this, where would you expect to have invariant points when taking the square root of a function f of x? Well, let's think about this. Can you think of any values that if we take the square root of them, they don't change? How about I give you a hint? There's only 2 numbers that this is true for. Only 2 numbers are their own square root. Can you think of what they might be? It's 1 and 0. right? What's the square root of 1? 1, because 1 times 1 is 1. What's the square root of 0? 0, because 0 times 0 is 0, right? The only number that we can multiply by itself and not change it is 1. Only number we multiply by itself and not change it is 0. And I say only, and then I said it twice, but the only two numbers we can do that for, right? Root 1 is 1. Root 0 is 0. So if we take the square root of a y value that was 1 to begin with, it's not going to change. If we take the square root of a y value that was 0 to begin with, it's not going to change. So the invariant points when taking square root of a function will be any points, points where the original function had a y value of 0 or 1. Okay, so we're looking for points like this. Something 0 or something 1. If points like that are on our original function, they're not going to change when we take the square root of the function. Because again, the square root, we're just taking the square root of the y values. So y value 0, square root of 0 is still 0. Y value is 1, square root of 1, still 1. So putting these ideas together allows us to sketch the graph of the square root of a function, right? This gives us a really good starting point. First, we're going to plot the invariant points anywhere y is 0 or y is 1 on the original function, because those points are guaranteed to be on the graph of the square root of the function. And then from there, honestly, you just take some square roots, right, to get a general idea of the shape, right? If you can see y is, again, I suggest anyway, you can cherry pick a little bit. Sometimes you got to do a little estimation with some decimals, but like if you see there's a place where y is 4, that's a good point to use to sketch your new graph, because the square root of 4 is just 2. Nice integer, not a weird decimal, right? If you see a place where y is 9, that's a good one, because the square root of 9 is just 3. Nice integer, no decimal. Take the square root of some y values to get the idea of the shape. Last thing we'll talk about before we jump into some examples here, the effect on the domain. Okay, now this is important to think about. Okay, remember, we're taking the square root of the function. We're taking the square root of the y values. Okay, what can we never take a square root of? A negative. So the radicand cannot be negative, right? Again, no number multiplied by itself can never be negative. And what a square root asks is what number times itself would give us this radicand. Right? So because we are taking the square root of the function here, the square root of the outputs, the y values, the domain of root f of x will only include values of x for which the original function, f of x, was positive. Or 0, I guess I should add in there. It's okay for it to be 0. Or 0. Okay? In other words, any x values that made y negative in the original function will be excluded from the domain of the square root of that function. The graph of the function just isn't defined there. We're trying to take the square root of a negative. Wherever y was a negative on the original graph, if we try to take the square root of that, it's undefined. It doesn't exist. You can't take the square root of a negative. If you ever forget that, if you're trying to draw it, you'll realize, oh, I can't take the square root of, -1 or the square root of -2. So you'll notice it. You'll catch it. If you try to square root the original y values, you'll see, hang on, that doesn't make sense. I'm trying to take the square root of a negative. Just to give you an example, let's say we wanted to take the square root of this function. Let's say it's, I don't know, y equals x squared minus 3, right? What are we going to do if we take the square root of this function? We're going to square root every y value. Right? Well, that works out just fine up here. You can take the square root of positive numbers. And up here, you can take the square root of positive numbers. But where you're going to run into issues is here. You can't take the square root of any of these y values. Why? Because they're negative, right? You can't take the square root of a negative. So the domain of the square root of this function, should have picked an easier number to go with, but this happens to be root 3, and this happens to be negative root 3. Okay, those would be the x-intercepts. The domain of this function, the original function, is all real numbers. But the domain of the square root of this function is not going to be all real numbers. It can't be anything in between those x-intercepts, because in between those x-intercepts, the original function is negative. The y values are negative. So we can't take the square root of them. So the domain of the square root of this function would be all values of x that are less than this x-intercept and all values of x that are greater than this x-intercept, but excluding the ones in between. Let's see how that looks with a couple examples here. So here we got a table of values. Our original function f of x is just x minus 1. And then we want to take the square root of this function, right, for g of x. So let's just first generally do it for x. Well, if f of x is x minus 1, then it's x minus 1 when x is x, keeping it general, not putting in an actual x yet. But what would be the square root of f of x then? If f of x is x minus 1, what's g of x? Well, it's the square root of f of x. So it really is this simple. It's the square root of x minus 1. That's it. Okay, so when x is 0, what do we have? We've got 0 minus 1, which is negative 1. So for g of x, that is the square root of 0 minus 1, which, that's the square root of negative 1. So it's undefined. Right? It's undefined. You can't take the square root of a negative. Okay? So even though 0 was in the domain of f of x, it's not in the domain of the square root of f of x. Okay? We would see the graph not go there on the square root of that function. Okay, when x is 1, we've got 1 minus 1, which is 0. Now, again, square root of 1 minus 1, that's the square root of 0, which is 0. Hey, invariant point. We've got an invariant point. Okay, just to point something out as well, folks, we can take the square root of the whole function. We also could have, if we wanted, just taken the square root of this output, right? What's the square root of 0? It's 0. It's kind of what we ended up doing there anyway. So when x is 2, we've got 2 minus 1, which is 1. Show you what I mean. We could just say, well, this function was 1. This one just takes the square root of the outputs, so it'll be square root 1, which is 1. Notice you get the same thing if you take the square root of the whole equation first. We'd have square root of 2 minus 1 when x is 2, which is square root of 1, which is 1. Hey, another invariant point. It would still be at, right? That point would still be at 2, 1, just like this one was. 2, 1, 2, 1. What about when x is 10? Well, then we've got 10 minus 1, which is 9. And we could do square root of 10 minus 1, or we could just kind of cut out that step and say, hey, I know the original function has a y value of 9. This just takes the square root of these functions' outputs, so square root of 9, right? Either way, we get to the same destination. Square root of 9 is 3. So that's not an invariant point. That one definitely changed, right? The original point was at 10, 9. Now, on the square root of this function, it's at 10, 3. But that checks out because the square root of 9 is 3. Square root the outputs, the y values. Okay, let's look at some graphs. So here we got a table of values. Our original function f of x is just x minus 1. And then we want to take the square root of this function, right, for g of x. So let's just first generally do it for x. Well, if f of x is x minus 1, then it's x minus 1 when x is x, keeping it general, not putting in an actual x yet. But what would be the square root of f of x then? If f of x is x minus 1, what's g of x? Well, it's the square root of f of x. So it really is this simple. It's the square root of x minus 1. That's it. Okay, so when x is 0, what do we have? We've got 0 minus 1, which is negative 1. So for g of x, that is the square root of 0 minus 1, which, that's the square root of negative 1. So it's undefined. Right? It's undefined. You can't take the square root of a negative. Okay? So even though 0 was in the domain of f of x, it's not in the domain of the square root of f of x. Okay? And we would see the graph not go there on the square root of that function. Okay. When x is 1, we've got 1 minus 1, which is 0. Now, again, square root of 1 minus 1, that's the square root of 0, which is 0. Hey, invariant point. We've got an invariant point. Okay, just to point something out as well, folks, we can take the square root of the whole function. We also could have, if we wanted, just taken the square root of this output, right? What's the square root of 0? It's 0. It's kind of what we ended up doing there anyway. So when x is 2, we've got 2 minus 1, which is 1. Show you what I mean. We could just say, well, this function was 1. This one just takes the square root of the outputs, so it'll be square root 1, which is 1. Notice you get the same thing if you take the square root of the whole equation first. We'd have square root of 2 minus 1 when x is 2, which is square root of 1, which is 1. Hey, another invariant point. It would still be at, right? That point would still be at 2, 1, just like this one was. 2, 1, 2, 1. What about when x is 10? Well, then we've got 10 minus 1, which is 9. And we could do square root of 10 minus 1, or we could just kind of cut out that step and say, hey, I know the original function has a y value of 9. This just takes the square root of these functions' outputs, so square root of 9, right? Either way, we get to the same destination. Square root of 9 is 3. So that's not an invariant point. That one definitely changed, right? The original point was at 10, 9. Now, on the square root of this function, it's at 10, 3. But that checks out because the square root of 9 is 3. Square root the outputs, the y values. Okay, let's look at some graphs. All right, so using the graphs of y equals f of x here and y equals g of x here, sketch the graphs of y equals root f of x and y equals root g of x. So remember, we're taking the square root of the function, the value of the function. When we say that, we mean its output, right? Its value at a given x. So we put in an x. The function's value is determined based on what the equation gives us out. So the square root of f of x, that just means we're taking the square root of the outputs, the square root of the y values, okay? So it really is, folks, all we're going to do is take the square root of the y values, keeping in mind that we can't take the square root of negatives. So, again, let's cherry pick a little bit. Let's pick, points that will be easy to take the square root of. So, for example, I'm just going to look for y values that are perfect squares. Because then when I take the square root of them, I get a nice integer and not an irrational number that's a little harder to, properly find on the graph. Sometimes you can't avoid it, but, find as many perfect squares as we can. And actually, I guess I'm jumping the gun a little bit here because really we can do even easier. We can first find some invariant points. So do you remember? What are invariant points when we take the square root of the function? Well, wherever y is 0 or y is 1, because the square root of 0 is still 0, and the square root of 1 is still 1. So 0, 0, and, whoops, no, that's x isn't 0. Y is definitely 0 there, but x is negative 9. Negative 9, 0, and negative 8, 1. Okay, so when I take the square root of those, I'll do the square roots in green, but those are going to be invariant. They're going to stay in the same spot. Okay, let's look at 0, 9. When I take the square root of 9, I get 3. So we should have a point at 0, 3, right? That point, when we take the square root of the function, it's going to end up there. That'll be the corresponding image point. Okay, I'm going to do 4 next, a y value of 4, because again, that's just an easy one to do, because the square root of 4 is just 2. No irrational numbers, no weird decimals to worry about. I can just say the square root of 4 is 2. So we'll have the point 0, 2. Okay, I'm just realizing this is a little bit in the way of where we're headed. 0, 3. Okay, so, oh my goodness, why do I keep saying 0? That's not 0. That's at negative 5. Negative 5, 4. I need more coffee. Okay. Negative 5, 4 becomes negative 5, 2. There we go. All right. So if we take a look at this, right, we know like we're taking the square root of a linear function. So it's just going to be something like root x. Obviously, it's not just root x because that's not what root x looks like. We can kind of actually see that it's going to be something like root x minus 9, right? Or x plus 9, sorry. Okay. But anyway, Don't need to come up with the equation because we can kind of see this is looking like a regular radical function graph, a regular kind of root x graph. It's going to do something like that, right? So that is the equation, or that is the graph, sorry, of y equals root f of x. What did we do? We just took the square root of enough y values to get an idea of the shape. The invariant points were very helpful. Now, I stopped here, right? Why did I need to stop here? Because why couldn't I keep going? Why couldn't I take the square root of this y value? Well, it's negative. Why is -1 there? What's the square root of -1? It's nonsense. It's undefined, right? You can't take the square root of -1 or -2. So our graph doesn't exist there. It's undefined, right? Y equals root f of x is undefined here. Didn't ask us for the domain, but we can see that the domain of y equals root f of x is going to have, right, the domain is going to be the set of all x's such that x is, well, greater than or equal to -9, because when x is less than -9, the original function is negative. Its y values are negative, so we can't take the square root of those. So root f of x will be undefined there. So x such that x is greater than or equal to -9. Didn't ask us for it, but nice to, think about it a little bit. Okay, let's try this one. Now we want to take the square root of g of x. So we want to sketch y equals the square root of g of x. So again, if y was g of x before, now we just want it to be the square root of g of x. Well, that means we just need to take the square roots of these values. Okay, so right off the bat, I'm going to switch up the order we look at this one. Where will y equals root g of x be undefined? Can you see anywhere where it would be undefined? Yeah, here, right? In between x being -2 and x being +2. Because for those x's, g of x is negative, and we can't take the square root of a negative. So for these x's here, right, here, maybe I'll just draw a box around it just to kind of show, right, y equals root g of x is undefined. Right? We can kind of see already what's going to be the domain of root g of x. Well, it'll be the x's less than -2 and greater than +2, but not in between -2 and +2. Because there, g of x is negative, and you can't take the square root of a negative. So just for fun, didn't ask for the domain, but let's just say that. All values of x such that x is less than or equal to -2, or x is greater than or equal to 2. It can be equal to because you can take the square root of 0, but you just can't take the square root of a negative. Okay, anyway, let's get back to actually sketching the graph of the square root of this function. I'm going to start with the invariant points. So those will be wherever y is 0 or 1. So here, that's going to be on the graph of root g of x. And so will that one. Okay, let's pick out some points. Again, I'm going to kind of choose carefully. So the x value might not be very nice here, but I'm still going to pick it because its y value is 4. And so it's pretty easy to just trace downwards and say the y value there will now be at 2, right? Because the square root of 4 is 2. So on the square root of this graph, we'll have a point there. Same x value, we leave those alone. We're not taking the square root of the x's, we're taking the square root of the function. Its outputs, its y values. Okay, let's try, how about 9 is another good one. So when I take the square root of 9, it's going to end up at 3. So right around there, right? This point here, ooh, this point here, whoa, not there, here, is going to end up, same x, but now it's at 3 for the y value, so right around there. Similar thing over here. Square root of 9 is 3. So our square root function is going to look like that. It's coming together. We can start to get an idea of the shape here. The square root of 16 is just 4. So here the y is on the original is 16. So square root of 16 is 4. So right around there should be another point. Okay, same thing on this side. Y is 16 here. Just about halfway between -4 and -5 on the x-axis. Somewhere around there. Okay, and we can kind of start to see the shape here. It's looking, you know, something like this. Something like this. Not perfect, but you get the idea. Okay, and so again, I'm just going to get rid of this just for now to look, right? This is what it looks like. It's kind of funky looking, right? There's nothing in between here, and then there's this extending that way and this extending that way. Cool, right? So just to kind of look at some of these, because A, I think they're really cool to look at, and B, just to show that all we ever do when we take the square root of a function really is take the square roots of the y values, and then, you know, remember that where y is negative, that just means our square root of that function won't exist. It won't be defined. So here's, you know, we looked at a parabola that was facing upwards. Here's a parabola that's opening downwards. And if I take the square root of that, it just looks like that. Notice where it stops. It stops where the original function in black started becoming negative, right? And if you look, invariant points are where y was 0 and 1 on the original function, right? A few places here, 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 and here. Cool, right? Okay, the other interesting thing, square root of 2 is about 1.41. You can test that for yourself on your calculator. Look, square root of 2, 1.41. Okay, let's look at a couple others. How about this one? Here's a funky cubic function. Here's its square root. Now notice again, look where the square root is defined and where it's undefined. Well, it's defined where the original function was positive because you can take the square root of a positive y. It's undefined here and here where the square root, where the original function had a negative y value because you can't take the square root of those, right? But again, noticing here, like when y was 4, x has now just become 2 on the square root of that function. See that? Cool, right? Okay, whoops, sorry. I had my pointer in the wrong place. There, right? Where y was 4, y is now 2 on the square root of that function. Okay, pretty cool. One more here. Let's look at a linear one. We saw a linear one. There's y equals x minus 9. Here is the square root of y equals x minus 9. Again, invariant points at 0, where y was 0 and where y was 1. And then just taking the square root. It's undefined when x is less than 9 here because the original function would be negative, right? As we go up, for example, when y is 9 on this function, what do you think y is going to be on the square root of that function? So when x is 18 on the square root function, what do you think y will be? Well, if it was 9 on the original, the square root of 9 is 3. So sure enough, when x is 18, y is 3 on the square root of this function, because y was 9 when x was 18 on the original function. Neat, huh? All right, so for this next example 3 here, we kind of got excited and we already did it just for fun. So I took it and, pasted it back down here. Again, right, the domain of y equals root f of x, it's the values of x for which the square root of f of x will be undefined, right? So it's where y is positive. These x values result in positive y values on the original function. So those x values can be part of the domain for root f of x, but these need to be excluded from its domain because for those values of x, the original function is negative, right? Same thing here. The ones between negative 2 and 2 need to be excluded from the domain for the square root of g of x because g of x is negative there. So we can't take the square root of those negatives, okay? Now what about the ranges? Well, our graph kind of shows us, right? Our graph shows us that it's the set of all y's such that y is greater than or equal to 0. Y is an element of the real numbers, okay? And what about for this one? Well, once again, the set of all y's such that y is greater than or equal to 0. That's common for some radical functions. It is not the only possible range that you could see, right? Just to come up with one example, what about a parabola that looks like this, right? That would not have a range once we took its square root. It would not have a range where y had to be greater than or equal to 0. I know that was the case for these two examples, but, suppose this happened at 4, right? Well, then when we take the square root of the function, it's going to end up looking something like this. Looks a little wonky. Then its range would be y would need to be greater than or equal to 2. So just a side note, just because those two happen to both have a range of y must be greater than or equal to 0, doesn't guarantee that's always going to be the case. It does come up fairly common in these. Whoops, there should be a square root there. And that's just because for any function that does become negative, it dips below 0. That's going to end up being the cutoff for the range, because you can't go lower than that and take the square root of it for the square root of a function. Okay, let's try out one from a diploma. All right, so often with diploma type questions, it's a good idea to read the question first. Doesn't always help, but sometimes it's nice to kind of give you the key information you're looking for. So the graph of the function y equals root f of x will have a domain of blank. So we want to know the domain if we take the square root of whatever f of x is. And there are blank invariant points associated with this transformation. So we're thinking about domain and invariant points when we take the square root of this function. I'm going to go ahead and guess we're taking the square root of this graphed function, but let's just read to make sure. The graph of y equals f of x is shown below. Okay, yes, I was right. The graph of y equals square root f of x is to be drawn on the same coordinate plane. We want to figure out what will be the domain of that square root function, not the original, the square root function, and how many invariant points will there be when we go from y equals f of x to y equals root f of x. How many points won't change? Well, we could start with whichever one we want to think about. How about the invariant points? That's a nice place to start. Where do we get invariant points when we take the square root of a function? Well, the y value has to not change when we take its square root. What number doesn't change when we take its square root? There's only two. It's 0 and 1, right? Square root of 1 is 1, square root of 0 is 0. So invariant points where f of x equals 0 or f of x equals 1. Again, since root 0 equals 0 and root 1 equals 1. They're their own square roots, okay? So how many places here do you see where y is 0 and y is 1 on our original function? Well, I know they didn't label numbers here, but they kind of don't have to, because this is going up forever. So like, no matter how our y-axis is scaled, these are going to cross 1, right? This arm will cross 1, this arm will cross 1. So I'm just going to say, like, let's pretend this is 1. I know it doesn't say that, but I see 2 there. It's going to have to cross 1. And I definitely see 2 here where y is 0, right? Sure, they didn't label it, but the x-axis is where y is 0, so 0 and 0. So I see 4 invariant points, right? Invariant points, 4 of them, right? 4 invariant points. Because if we take the square root of 1 or 0, it's still at 1 or 0 for the y value. So that right away narrows us down to 2, like 2 choices, I mean, because it can't be 2, so it can't be B or D. So it's either A or C. So if we take a look, A has us saying x has to be less than negative A or greater than B. In other words, below, like outside of the x-intercepts. This one says x needs to be between negative a and b, so between the x-intercepts. Well, what do you think? Which of those 2 options seems right? Let's take a look. Okay, so why would we have the restrictions on the domain anyway, right? Why isn't it just all real numbers like the original function would have a domain of? Well, because the original function has negative y values. We can't take the square root of negative y values. So wherever the original function had negative y values, which is between them, those are not going to be part of the domain of the square root of the function, right? Between the x-intercepts is what we have to exclude from the domain, okay? Root f of x will be defined here. Sorry, undefined here. Since f of x, the original function, is less than 0 for these x values, right? And what are those x values? They're the ones between negative a and b, right? So essentially, we need to domain must, well, root f of x domain must exclude x's such that negative a is less than or equal to x, which is less than or equal to b. In other words, we need to include the x's that are less than negative a and greater than b. So our domain would be, I see it in our options, our domain would be the set of all x's, root f of x domain, such that x is less than or equal to negative a, or x is greater than or equal to b, because those are our two x-intercepts. One's called negative a, one's called b. So our answer would be a, right? A looks good to me. 4 invariant points, and that would be our domain. All right. So if f of x equals x squared minus 1, we want to algebraically, that's important, that means, showing mathematical steps on paper with algebraic reasoning, not just putting it in your graphing calculator and saying, I found them, okay? If you do that on a diploma and the question asked for you to do it algebraically, they're going to give you a 0 on that question, even if you got the right answer. They don't just say that for fun. That means they want you to demonstrate your algebraic methods. So determine 4 invariant points. Okay, we're looking for 4 invariant points and the domain of y equals root f of x. Let's start with the invariant points. So again, we get invariant points if we're taking the square root of this function, which we are. We're going to get invariant points wherever the original function, f of x, wherever, oh boy, I can't spell today, wherever the original function f of x equals 0 or 1. So we just need to find what we need to find is the x values that give that, right? What x's make this equal 0 or 1? Because to find the invariant points, I mean, we know right away the y values are 0 or 1, right? But that's no good without the x values. So I shouldn't say it's no good. It's good to have the y values, but it's a point. It also has an x value. So find x's that result in this. In other words, what values of x will result in y being 0 for our original function? So let's just do, how do we make f of x equal 0? How do we make f of x equal 1? Well, we're just solving an equation now. How do I make it so that 0 equals x squared minus 1? We'll add 1 to both sides. 1 equals x squared. And now we are going to take the square root of both sides to solve for x. But we took that square root, so we have to recognize it could be, right? The square root of 1 is 1, but the square root of 1 is also negative 1, because negative 1 times itself is 1, right? Negative 1 squared is positive 1. So plus or minus 1 is x, right? So x could be plus or minus 1. What is y when that happens? It's 0. And then when we take the square root of that, it'll still be 0. So our invariant points are 1, 0, and negative 1, 0, right? When x is negative 1, negative 1 squared is 1, 1 minus 1 is 0. So taking the square root of that, it's still going to be at the point negative 1, 0. Same logic goes for 1, 0. 1 squared is 1, 1 minus 1 is 0. Take the square root of that y value being 0, and you're still at x of 1, y of 0. So there's 2 down, 2 to go. How do we make x squared minus 1 equal 1? Well, I'll add 2 to both sides, or sorry, add 1 to both sides to start solving for x. That's going to give me 2 equals x squared, and now take the square root. Square root, and plus or minus the square root of 2. I would not put that into your calculator and get the irrational number. Root 2 is perfectly valid. That is an exact value. It's not rounded like you're going to have to do if you try to round the irrational 1.41 repeating forever that you get if you take the square root of 2. We know from working with radicals in the past, sometimes it's best to just leave it as root 2. So that's what I'm going to do. That's a perfectly valid number. Okay, so we know that when x is negative or positive root 2, y will be 1 on the original function. And so when x is root 2 or negative root 2 on the square root of the function, y will still be 1, because the square root of y being 1 is still 1. So that gives us 2 more points. Root 2, 1, and negative root 2, 1. Right? Can always double check our work. Root 2 squared would be, root 2 squared would be 2. 2 minus 1 is 1. Right? So when x is root 2 on the original function, y is 1 on the original function. Meaning that on the square root of the function, when x is root 2, y is still 1, because the square root of 1 is 1. Same logic here. So there's our invariant points. Invariant points. We found all 4 that they asked us to find. Okay, what about the domain? Well, we need our domain, right? We know the domain for the square root of the function will just be wherever the original function was greater than or equal to 0, right? Wherever this was negative is not part of the domain for the square root, because you can't take the square root of the negative. So the domain of root f of x is just all values of x for which, I really can't spell today, winch, for which f of x is greater than or equal to 0, right? Because then there's no problems with taking the square root of it. Root f of x will just be root of those y values. But where f of x is negative, that's where we have a problem. That's where root f of x is undefined. So that's, that's an equation for us, or sorry, not an equation, an inequality for us to solve. Where is f of x greater than or equal to 0 is just where is x squared minus 1 greater than or equal to 0? Because x squared minus 1 is what f of x is equal to. So where is x squared, add 1 to both sides, greater than or equal to 1? Okay, and now we would take the square root of both sides. Now, in doing that, we are opening up 2 possibilities, right? There's the negative option and the positive option, right? So we kind of have to branch off into 2. And we can even just think about it. How is x squared greater than or equal to 1? Well, it could happen if x is a number that's greater than 1, but it could also happen if x is less than a number that's negative 1, right? Negative 2 squared would be positive 4, which is greater than 1, right? Negative 10 squared would be positive 100, which is greater than 1. So we have 2 options here. X could be greater than or equal to positive 1, or x could be less than or equal to negative 1. Both of those are valid solutions. So when we take the square root, again, we have that plus minus situation to think about. And because of the inequality, there's one where we, take the positive and don't flip, take the negative and do flip the inequality. Okay, so our domain, that tells us our domain. X needs to be outside of 1 and negative 1. So domain for root f of x is the set of all x's such that x is less than or equal to negative 1. Sorry, there's sirens going on in the background. Hope that's not too loud. Or x is greater than or equal to positive 1. X is an element of the real numbers. Okay. In interval notation, if you like, you could say it's from negative infinity up to negative 1. And then we use this symbol union. It's just showing that we can't write it as one continuous interval because it doesn't go from negative infinity to infinity, but it does go from negative infinity all the way up to negative 1, and then there's a break, and then it goes from 1 all the way up to infinity. That's how we could write that one in interval notation. And there we go. There's the domain for that one. And that's the last example for the notes today. So all it's left to do is practice. I would recommend starting with this one while this square root of a function stuff is fresh in your brain. It's a little bit about matching the graph to its square root. Kind of fun, okay? And once you're finished up with that, you can do the rest of the practice that you might have left until now. And yeah, don't forget to reach out with any questions, concerns, whatever. Book a meeting or send an email. Always happy to help. But there we go. Lesson 4, donezo.